Hi Year 12, this is our second lesson for the topic Applications of Differentiation. So previously we've looked at the sign of the first derivative, increasing, decreasing and stationary points. We looked at the first derivative test and then we discussed local and global maxima and minima. Now this lesson we're going to look at the second derivative, so the sign of the second derivative, concavity, second derivative test and points of inflection. To find the second derivative, all we do is differentiate the first derivative, and there are several permissible notations. We have f double dashed of x, y double dashed. We've got this rather strange notation, d squared y dx squared, and it almost looks like I've put the squared in the wrong position. But it comes from d dx of dy dx, the derivative of dy dx. So you can see where the d squared comes from. Now technically we should have brackets around the dx, but we don't do that. So it is d squared y dx squared. Let's look at an example. Find the first and second derivatives of y equals sine squared x. Now remember, sine squared x can be written as sine x all squared, which is going to help us find the derivative because this is a chain rule. Our outer function is a power function, our inner function is a trig function. So let's do the derivative. The 2 comes down, sine x all to the power of 1, multiply by the derivative of the inner function, which is cos x. So our first derivative is 2 sine x cos x. Now the second derivative is going to be a product rule. So we're going to let u equal 2 sine x and v equal cos x. The derivatives are u dashed is 2 cos x, v dashed is negative sine x. And constructing the product rule, we have d squared y dx squared, because it's the second derivative, is equal to u times v dashed plus v times u dashed, which is here. And tidying it up, we get 2 outside of cos squared x take away sine squared x. Now last lesson we looked at what the first derivative is testing, and that's increasing, decreasing or stationary. The second derivative tests the concavity of the curve. Now remember that concave up curve is a minimum and a concave down curve is a maximum. Now let's have a look what's happening with the gradient of the tangents for a minimum. So they start off at -2, then -1, 0, 1, 2. Can you see that increasing? So the rate of change of the first derivative is positive. The second derivative is positive. Make sure that makes sense to you. Here's a maximum. What's happening here? We've got a gradient of 2, then 1, then 0, -1, -2. The gradients are decreasing. So the rate of change of the first derivative is negative. Now an inflection occurs when there is a change in concavity. So if we go from concave down to concave up, or from concave up to concave down. Let's have a look what's happening with the gradients. So what's the rate of change of these gradients? We've got negative coming through 0 up to positive, so it's increasing here. And then here we've got 2, 1, 0, it's decreasing here. So it's changing from positive or increasing to negative or decreasing. So at this point here, this inflection, our second derivative is equal to 0. And then finally we have what's called a horizontal inflection. And that's a stationary point, so the first derivative is equal to 0, where there's also a change in concavity. So we're going from concave down here to concave up, but it's stationary at this point. Here we're going from concave up to concave down. Let's have a look what's happening. Here we've got gradients that are increasing until we get to 0, and then they're decreasing. So we do have a change in concavity, but also our first derivative is 0 at this point. So let's revise. If the second derivative is positive, then the curve is concave up. Negative, the curve is concave down. 0, there is a change in concavity, or what we call an inflection. Let's look at an example. Show by using the second derivative that the curve y equals ln x is always concave down. So we want to differentiate this twice. Well, the first derivative is just going to be 1 on x, which is the same as x to the power of -1. Second derivative, it's just a power rule. I'm going to bring this -1 down and then drop that power by 1. So negative x to the power of -2. which is the same as -1 on x squared. Now, we want to show that this is always concave down. In other words, we want to show that the second derivative is always less than 0. And it is, isn't it? Because this is a square, so that's always going to be positive. 1 is positive, so this is always going to be negative. Therefore, y equals ln x is always concave down. Example 2. When does the curve y equals x squared multiplied by x minus 1 change concavity? So again, we want the second derivative and we want to put that equal to 0. So easiest way to differentiate this is not the product rule, it's to expand it out first. So y is equal to x cubed minus x squared. Differentiating, we get 3x squared minus 2x, and differentiating again, we get 6x minus 2. So let's put that equal to 0. 6x minus 2 is equal to 0, x must be equal to a third. So there's a change in concavity at x equals 1/3. So the good news is we can use the second derivative to test the nature of any stationary points, and it's much easier than using the first derivative test. If the second derivative is greater than 0, the curve is concave up, therefore it's a minimum. If the second derivative is less than 0, the curve is concave down, therefore it is a maximum. Here's an example. Find the stationary points on the curve y equals x squared multiplied by x minus 3 in brackets and determine their nature. So we worked out the first derivative of this function before. It is 3x squared take away 6x, and we want to solve y dashed equals 0. So 3x squared takes 6x equals 0, factorise, x is equal to 0 or 2. We want to find the stationary points, so we need to know the y coordinates, substitute 0 back into here, then substitute 2 back into here. So at x equals 0, y is equal to 0, so that's the point 0, 0. At x equals 2, y is equal to 4 lots of -1, which is -4, so that's the point 2, -4. Now let's find the second derivative to test the nature of those points. Second derivative is 6x take away 6. And we're just going to do both of those in turn. So at x equals 0, the second derivative is -6, which is less than 0. Therefore, concave down, it is a maximum. At x equals 2, the second derivative is 12, take away 6 is 6, greater than 0, therefore concave up, a minimum. Therefore, there is a maximum at 0, 0, and a minimum at 2, -4. Now, if the first and second derivatives are both 0, then there is a possible horizontal inflection. And I say possible because the second derivative test has a flaw, which I'm going to show you in a second. Here's an example. Show that the first and second derivatives of y equals x cubed are equal to 0 at 0, 0. So first derivative is 3x squared. At x equals 0, the first derivative is equal to 0, therefore there's a stationary point. Second derivative is 6x. At x equals 0, the second derivative is equal to 0, therefore there's a possible horizontal inflection at 0, 0. So it doesn't always work. Find the stationary point on the curve y equals x to the power of 4 and determine its nature. Okay, first derivative is 4x cubed. Solving y dashed is equal to 0, I get x is equal to 0. So there is a stationary point at 0, 0. Second derivative is 12x squared. Well, at x equals 0, the second derivative is equal to 0. Therefore, there's a possible horizontal inflection. So when we get the first derivative equal to 0 and the second derivative equal to 0, the second derivative test is inconclusive. Okay, sometimes it works and sometimes it doesn't. We need to use the first derivative test to verify. So we have a possible horizontal inflection at x equals 0. Let's test either side. We're going into the first derivative. Put the -1 in, we get -4. Put the 0 in, we get 0. Put the 1 in, we get +4. Drawing it up actually isn't a horizontal inflection, it is a minimum. So let's finish off by describing the rate of change. The curve below shows the population of seals on a particular island over time. State the sign of the first and second derivatives and describe the rate of change. So the curve is increasing, so the first derivative is positive. It is concave down, so the second derivative is negative. Therefore, we can say that the population is increasing, but at a decreasing rate. So here's the 4 curves that you need to know. Let's go through them. Here we have an increasing curve, so first derivative is positive. It's concave up, so second derivative is positive. We say the quantity is increasing, the rate of change is increasing, and it is speeding up. Here we have an increasing curve, the first derivative is positive. It is concave down, the second derivative is negative. We say the quantity is increasing, but the rate of change is decreasing, it is slowing down. Now these next 2 are going to cause some concern. In both cases, the first derivative is negative. We can tell that, it's going down. Here we have concave up, so positive for the second derivative, concave down, so negative for the second derivative. And we say this one is slowing down, and we say this one is speeding up. But here's the problem. Here we say the quantity is decreasing, but the rate of change is increasing because it's going from a negative gradient and becoming less negative. And in this case here, we say the quantity is decreasing, but the rate of change is decreasing. It's getting more and more negative. And that's contrary to what you think. I've got 2 past exam questions that I want to show you, and let's see whether we can figure out the difference in the language. The particle is moving along the x-axis. The displacement of the particle at time t seconds is x meters. At a certain time, the velocity is equal to -3 meters per second, and the acceleration is equal to 2 meters per second squared. Which statement describes the motion of the particle at that time? So we've got various options about whether the particle is moving to the left or the right. And remember, if velocity is negative, then the particle is moving to the left. So it's either going to be B or D. Now the acceleration is equal to 2, and the velocity is equal to -3, and they have different signs. And remember in year 11 that I taught you that if acceleration and velocity have opposite signs, then they are fighting against one another, and the particle is slowing down. So out of B and D, it's actually going to be D. Here's the other question. The graph shows the displacement x of a particle moving along a straight line as a function of time t. Which statement describes the motion of the particle at point P? So we have various options about the velocity being positive or negative, and various options about the acceleration being positive or negative. So at point P, what's the velocity doing? The velocity is the first derivative, so that's testing, increasing, decreasing, or stationary. What's it here? It's decreasing, so it's either going to be A or B. Acceleration is the second derivative, that's testing concavity. So at this point it's concave up, so our acceleration is positive. So the answer is A. So what's the main difference in these 2 questions? Can you see it's this word, speed, as opposed to acceleration? So remember, speed doesn't have a sign. It's not positive or negative, whereas acceleration does. Now, these questions are almost identical. In both cases, the velocity is negative, so the particle's moving to the left. In both cases, the acceleration is positive, so they're opposite signs. So in this case, we're asked about the acceleration, which is positive. Here we're asked about the speed and whether the acceleration has the same sign as the velocity or opposite signs. Hope that makes sense to you. Here's another past HSC question, a little bit more recent. The diagram shows part of the y equals f of x curve, which has a local minimum at x is equal to -2, a local maximum at x is equal to 3. Which of the following shows the correct relationship between f double dashed of -2, f of 0, and f dashed of 3? It's a really good question because it's testing your understanding of these 3 things. So let's go through them. F double dash of -2. Second derivative tests concavity. At this point here, the curve is concave up, so the second derivative at -2 is positive. F of 0. This is the y coordinate. Can you see that that's negative here? We don't know exactly what it is, but it doesn't matter. F of 0 is less than 0. And then finally, f dashed of 3. This is testing increasing, decreasing, or stationary. At this point, it is stationary, so f dashed of 3 is equal to 0. Now just putting them in order, this is the smallest, then followed by this one, followed by this one, so our answer is A. And one more. Now this question is from quite a few years ago, and I'm not going to give you the answer till next lesson. The diagram shows a 10 centimetre high glass that is being filled with water at a constant rate by volume. Let y equals f of t be the depth of water in the glass as a function of time t. Part 1. Find the approximate depth y1 at which dy dt is a maximum. Now this just means when is the depth increasing the most rapidly? And then find the approximate depth y2 when dy dt is a minimum. When is the depth increasing the slowest? And then part 2, assume that the glass takes 5 seconds to fill. Graph y equals f of t and identify any points on your graph where the concavity changes. Now just a little hint, you won't know the exact times y1 and y2, so just mark them as y1 and y2 on your graph. Okay, that's it. Our next lesson is on curve sketching.